Hello guys, good morning everyone. Welcome to another episode of XahTV Show. So today we are going to do Wolfram language coding, and I'm going to redo these images. I'm gonna redo this one and this, all the conic sections and torus, and I'm going to do some of the simple plot of surfaces that can be represented by a parametric equation. So Wolfram language Mathematica. So that's we are going to do. Today's 2021, July 23rd. Okay, welcome. If you have comments and questions, post it. Okay. Good morning, Bart. Okay, so start Wolfram language. That's the first stop, and then we're gonna just code it. So in this talk show, you might learn some practical Wolfram language basics, really basics. Okay, so the first thing, let's do sphere. Okay, so I'm going to basically redo these. This is done about 15 years ago, and I'm going to redo them. So today's talk show, so we have a link to sphere. And okay, so we're gonna regenerate and update my website, and I'm gonna show you the Wolfram language code. Okay, so go to Wolfram language, and how do you do this? Okay, parametric plot. There it is, the formula right there. So paste it. Okay, let's just paste it. There it is. So we have a sphere with a little bit gap. Why the gap? Because I kind of like the gap because the gap shows you the start and end positions of the parameters here. You see, so if this 0 to pi, so the formula is cosine. This is the formula. Three functions. The first part is x, then the y part, then the z. And the u and v are two parameters because this is a two-dimensional surface. You need two parameters to cover it. And u and v are the parameters, and u goes from 0 to 3. So if we change 0 to 3 instead of to 0 to pi, then you see it fills up the gap. No, 0 to 2 pi. Wait. Okay, 0 to half pi. So instead of 3, let's say 0 to half pi. Yeah. Wait, what's going on? It should be 2 pi. Pi is 3.16, but okay. So let's change this to pi too. So why don't we show a, let me show you this, okay, manipulate. Okay, and we're going to plot this and plot point. So let's remove the plot point. The plot points tells Wolfram language how many points to plot for u and how many points to plot for v. The two parameters. So right now we have 10, 20. Maybe that's why the grid does not get aligned up. So if we remove that, then it's automatic. Then here we want 2 pi. Do it. Okay. Now you see, now the grids are aligned. So now all we have to do, remove the gap, is change the 3 to 2 pi, yeah. There we have it. Okay, then we got little problems. Why is the grid not aligned? I'm not sure. You see the grid here, it's not refined there. So Ztron Crazy, good morning. Haven't seen you for a while. You seem relaxed now. Woke up properly. Yes, kind of. So let's do the manipulate. So we want to find out why is the grid not aligned, and one of the easiest way to see the parameterization of a surface, which parameters determines which patch of the surface, is to use dynamic visualization. So you can have a slider that changes the parameter and see the visualization on the fly. So that's what we are going to do. So we're going to cut this formula we want to plot, cut it and paste it here, and let's magnify so you can see bigger. Okay, and remove the plot points, and now the U, let's say U max. Okay, so U goes from 0 to U max, V goes from 0 to V max. Okay, then we are going to say, then we are going to say a list. So this is U max from 1 to 3. Okay, so that's U max. Then V max goes from 0 to from 1 to pi, let's say 1 to 2 pi. Okay, let's evaluate it. Okay, we got error. Why is that? The function value 0 V max. Oh yeah, so we got this should be V max, not U max. Okay, V max. There we have it. Okay. Now let's magnify. So U, let's increase U. So U is kind of the horizontal. It only goes half of the sphere. Okay, so you see that's a U part. U only goes half of sphere. U to U max, V to V max, and U max 1 to 3. So let's check. Let's see what does V do. So V goes to okay, this parameterization, I don't like it because it's going from, it's doing weird. I mean, it's covering the sphere, but in a weird kind of way. Can we make a parameterization of the sphere such that it kind of swap the U and V position and doesn't do this weird thing? I think it's possible. But okay, so I don't know what's going on. So let's say 6, let's say 3 here. So maybe that. Okay, so okay, problem. Hi gamer breakfast. Hi breakfast. Okay. So we succeeded in plotting the sphere, but the thing, if you really want a pretty page, that lies in the detail. There are so many ways to plot the sphere. Let me tell you something about math. Okay, the parameterization of a surface. So you want to plot a sphere, and one of the first thing you want to find is a parametric formula. Now there are more than one possible. There are many ways to have a parametric formula to plot a sphere. They cover the sphere in different ways. So anyway, so let's see what's the problem of our current one. So the first one, the U the U parameter goes from 1 to 3. So that should cover it, okay? So U parameter goes to 1 to pi. So this should be, the max is pi, okay? Wait, but if you change it to pi, what's going on? U from 1 to pi. Wait, let's say 4. I'm not sure what's going on here exactly. So let's prettify the code a little bit. So this way it's easier to read. So U max, let's say 324, okay? So first of all, we focus on the U parameter, 324. So the first parameter actually should be, you know, it kind of just cover the horizontal rotation. Let's see the second parameter. So the second parameter is more about vertical, yeah. Oh, okay. So you see, this parameterization sucks because the second parameter is not just about vertical, but it's also, you see, it's also covering part of the U parameters thing. Okay, so that is why we get this kind of funky thing. So the best thing to do is just look up Wikipedia, see what parameterization they give. Okay, so let's go to Wikipedia. Okay, Wikipedia, and what does it say? Sphere, okay, it gives you a kind of a transparency. We can do that as well. And so what parameters? So you also have a equational formula. So here is the parameter. Let's see if we can copy that. Let's see. Yeah, this is tech fuck. Okay, so that's not helpful. So we rather just write it ourselves. So 3xyz, okay? xyz. So x is r sine alpha. Theta and alpha, okay. That's phi, okay, that's phi. Okay, so theta is u and phi is phi, okay, let's see that. You need r is the radius is 1, so let's ignore that. Okay, so that's the first thing. The second thing, r sine, okay, sine. The third parameter is cosine theta, okay, cosine at theta is u, okay. So this is the alternative formula. So let's try that. Okay, so let's try to manipulate this alternative formula, okay? Hello, Beatrix. So copy that. This is the formula, and this is U max, this is V max. Okay, do it. Now let's see. 3 to 4. Okay, now it also, so 3 to 4, the U should be 2 pi. Okay, so U, yeah, okay. And the V, let's see, what does V do? Yeah, that's a better, now that's a much better parametric formula. Okay, so V will be 2 pi, not 2 pi. Okay, so let's try that. U does that thing, V does that thing. Fantastic. Now this is a better formula and actually simpler too. Let's see, sine, cosine, sine, sine, cosine. Okay, what did we have? We had, okay, it's about the same. You know, if we swapped U and V, we probably get it. Yeah. So anyway, it's, you know, it's probably the same formula. Okay, so that is what we want. Okay, now let's do some Emacs to replace this image. So we got the graphics here. So we are plotting some Wolfram language, using Wolfram language to plot some surfaces today. Let me show you. Okay, so you know, we are going to plot these 1, 2, 3, 4, 5 and sphere and torus, about 7 surfaces today. So the first stop is sphere. So we done sphere, and now the next step is to replace this image. Okay, now go back to Wolfram language. Now let's copy the code. So this is the code we want. So let's put it here. Vmax. Okay, so what's a Vmax? 2 pi and pi. Okay, and here is pi. Okay, do it. Fantastic. And what kind of orientation do I want? Let's see, compared to here. Okay, so you do want to show some kind of the top. Let's just do that. Okay, now why is there some, I don't know if you can see it, there's some glitches on the ball. Yeah, there's some glitches. Now there is some transparency. Let's try transparency. Okay, so this is what we want. Let's try some transparency. So we want to see options for parametric plot. Okay, so let's look at the documentation. Parametric plot options. So axis, boundary style, color function, evaluate mirror, exclusions, automatic endpoints, or V curve to curves to exclude, exclusion style, max recursion, mesh style. Let's see some examples. Dark mesh, gray mesh, light mesh. Themes that affect 3D surface include what themes? The arguments applied to functions in mesh functions and region functions are this and that. Functions in color functions. Mesh functions, mesh automatic. Okay. So here's some examples. Here, opacity, okay, plot style directive green opacity. So let's copy that. Let's see what that one. Okay, this one, very good transparencies. Okay, yeah, this is some sort of propeller, pretty. So plot style directive, let's try that. Okay. Okay, I decided I want, let's just use these. Okay, let's see red, specularity, specularity, remove, let's see what happens. Okay, so let's try red. Okay, what? Oh, okay, specularity must be inside the directive. So here is the plot style, and plot style, a rule, plot style go, specify plot style by this directive. This directive is red, opacity, and specularity that controls the surface. Okay, red does not look good. Yellow, not good. Okay, now there's another problem. You see this grid line. Wait. Okay, so lots of refinement issues. You see, I don't want the grid line to have some kind of, you see, this gap. So I guess now that's when you need plot points. Okay, comma. Okay, there's still a gap. Okay, so minus 0.0001 minus a little bit small number. Plot point 60. What the? Okay, now we need to control not plot point. Plot point is just how smooth it is. We want instead, you see, if you change plot point to 5, then it becomes that. If you change plot point to 60, it's very smooth, but however, the grid line is still, a problem. So you need a directive, you need a option to control the grid lines. Okay. What's going on? So, what's going on with the? It's not going back. Okay, there's a bug either with Windows or my auto hotkey is fucking things up. Alt space Alt space doesn't work. Alt space, I was hoping it to bring the menu. You see, now I cannot shrink the window. That's the problem. That's the problem here. Alt space doesn't work. What is this? Even Windows down arrow doesn't work. So let's save this. Okay. Sphere. Save it to desktop. Okay. Save. Close it. Okay. Now open the desktop. It get back to this maxed window. I cannot get out of. Yeah, okay, close it. So now what can we do to solve this problem? We are going to do surgery on the file itself. So go to desktop directory, Emacs comes to the rescue. So here is the file sphere. Let's open it up and let's remove the cache and shit. Cache shit. Okay, save it, close it. Now reopen in Wolfram language. Okay, there is a Windows problem. Let's do it again. Okay, so go all the way down. So here is the internal cache information. You see, delete notebook outline, delete. Okay, so close it, save it, shrink the window, go to desktop, open it. What the F11 does not work. Close it. God, I must be sure. Let's open in Emacs again. Let's see what's going on with this box data. So this is the postscript information for the, you know, the part here you see, that's the postscript format for the image, and encoded in what's the name, but anyway, I want to fix the Windows problem. Windows size full, okay? So delete that. Windows margin, delete that. Windows magnification, delete that. Okay, save it, close it, and we can open in external. Open in external. There it is. Okay, that's a Windows option. Okay, so we still haven't fixed the. We still haven't fixed the grid problem. So we need to look for options for the grid. So okay, let's do that. Options at Parametric Plot 3D. Okay, let's see options. So here are all the possible options for Parametric Plot 3D. and we want to look for mesh functions. Okay. So what is the option for mesh functions? It's an option for plotting functions that specifies functions to use to determine the placement of mesh divisions. Okay. So mesh functions, it's an option, and the argument is two functions. Specify that meshes corresponding to x and y coordinates should be constructed. So the first function controls the mesh around the x coordinate. Let's see some examples. Okay, so mesh is a simpler option. You see here mesh that specifies how many meshes to draw. So let's just try that. Let's say 9. Do it. There it is. Now let's say instead of 9, let's say 3 and 5. Do it. Okay. So the first element is the horizontal lines, the number of horizontal lines. So if we say 30, you see, we don't have a problem with that. The problem is the vertical lines. You see, it's missing a line. So here, instead of 5, let's say 6. Okay, that doesn't help. Let's say 20. You see, that doesn't help neither. So the problem, I kind of know what's the problem. The problem is that when you have the parametric surface, the problem is with the, you see, this is a place where the parametric start and end position collides. So in order to fix that, we can, we can either overlap it a little bit, then we, so again, what is V? Yeah, so the problem is V here. So if we say pi plus pi divided by 10, okay? So the vertical mesh 10. Yeah, you see, now that fixes up the problem, but however, you can see there's an overlap here, and it's actually more opaque than the rest of it. You see, if we say opacity 5, you see there's a particular strip. Okay, how do we fix this? Jesus, a simple thing. This, I kind of know what's the problem, but the problem, you see, the way, the old way, this is Wolfram language 20 years ago. This is much simpler. You don't have this problem. But however, you can see this image. They are just a bunch of polyhedrons. Each of the square is actually a polyhedron. But in the current version of Wolfram language, it's not just polyhedrons. You see, so in the old Wolfram language, the mesh is simply the edges of the polyhedron. There's no extra concept of the mesh, the grid lines. You simply plot each polyhedron, and those are the edges that forms the grid on the surface. But with advanced Wolfram language, the concept of grid on the surface and the actual polyhedron forming the surface is now separate. So the surface is just the surface. Then you can specify what kind of grid you want on the surface. Okay, so it's more advanced, but however, you run into the problem is that, it's missing it's kind of, the grid is not, it's kind of missing a line in the grid. So how do I fix that? It's probably pretty easy to fix that. But however, I need to look into, I need to read the documentation, like spend 20 hours, 20, 30 minutes probably to understand that. Okay, so let's skip that and let's do something. Let's get on to something else, shall we? Comments, okay? Okay, but anyway, let me just use one of these image. Okay, let's just use one of these images. So now let's not say opacity. Okay, opacity 0.95. So we kind of try to fix this hack. Okay, so pi plus pi over 10. So let's get it a little bit overlap, and meanwhile not making it transparent, so that you don't actually see the overlap. So we hack to fix this. Okay, so now we just determine the orientation we want. Okay. Now we export these graphics. Save graphics as PDF. No, I don't want PDF. I want PNG. So Wolfram language can save PDF, PNG, BMP, or web page HTML, or TIFF, or other formats, Windows meta file, and JPEG, and even Pixar, whatever that is. Let's say PNG. TT sphere, okay? Save that in desktop, okay? Save it. Now, another way to capture this image is just use capture it manually, okay? Screenshot. Let's do both ways and see which way is better. Okay, so now we have, if you update, you can see here is a saved image, open Emacs, there it is. And we also captured, using this program, ShareX, which is a great Windows program for screen capture. Okay, now let's go back to the sphere page, okay? Let's go to the sphere page, make a backup, show in browser. Then let's start to edit. Let's change the, okay, let's call this command that will move the image to, okay, not such file directory. So here is the directory, surfaces sphere. Okay, so here is the old image. Close it, close it. Save this here. It's trying to optimize the PNG file here. Shrink, show in browser, show in browser. There it is. Now go to desktop. Okay, so this is actually the screenshot we did. Now let's try to do the other. Okay, OptiPNG, show in browser, magnify. So we have two images. Now which is better? You see these glitches, another problem. You see these glitches on the sphere? God. You see, old Mathematica 20 years ago, it's pretty basic, but the new one with anti-aliasing and all that feature, but now you have got these dirty spots on the ball. Anyway, now let's tech geek about these two different image format. One is exported from Wolfram language, the other one is screenshot. Let's compare their sizes. Let's see which one is better. So you can see, so this is old, and this is, which one is this from? The first one is screenshot. Okay, so this is from screenshot. Let's see, 145 kilobytes. Okay, then the second one is 146 kilobytes. Okay, let's put them here. Okay, so we can have them side by side. Are they, which one is better? It's about the same, but you have all these spots on the sphere, dirty spots on the sphere, no good. So let's remove one of them. Okay, we don't need, and let's copy that here and show. So which one do you think is better? How did you install Emacs on Windows, with .exe or with zip? I downloaded from the GNU Emacs website. So you just go to XahTV Emacs tutorial, where to download. This is where I follow the instructions here. That's how I get Windows GNU Emacs .exe. Well, what do you mean by .exe or .zip? It's a zip file. .exe can be zip file or can be GZ or can be, what do you mean? So anyway, so that's where I download Emacs. Okay, so back to this. Oh, we already talked for 52 minutes. And we only did the sphere. I want to, let's go on and do, I want to do some of the other interesting things. So this is a hyperbolic paraboloid. It has this interesting property where on this surface, for every point on the surface, there is a line on the surface crossing it. So in other words, this surface is made up entirely of lines, so you just have lines and you can form this surface. It's interesting because usually you don't, when you have a surface, you don't have that, you typically you don't think of that. For example, sphere, there's not even one single line on the surface. So, but this is one of them, so this kind of surface where the entire surface can be generated by moving a line is called ruled surface, RUL, it's like a ruler, ruled surfaces. And there's a Wikipedia article on that. So this is a ruled surface. This is also a ruled surface, you can see. And you can see many baskets made out of this thing forming the surface. So in one way, it's just lines. But if you looked at it from the traditional way, you see, if you look at this surface, you don't think of it as lines, but it actually is. So we have many architectures and towers made of, forming this surface by having lines underneath. And then here's a funny gear for a black axis. Okay, my pages, all these pages are pretty old, like 20 years old. It was bleeding edge 20 years ago, but today you can find a lot better websites doing these things. For example, this, do it yourself, print 3D toy. You can find this print 3D, model to print it yourself. And this is Second Life. It's a Second Life is amazing. Okay, so there's lots of mathematics in Second Life. So anyway, so this is another rule surface, and you can see. Okay, so right, I'm just like talking about some random math stuff because like taking a break. So here you can see the what is this power station? You know, they are chimney. Those smoke are not smokes. Those are steams. You see, okay, it's much, you know, actually lots of repetition here. So anyway, that's why I want to update my website to make them modern now. And I was hoping to do many of these in JavaScript. Okay, so back to Wolfram language. Let's plot this, okay? So this is gonna be more than 1 hour. Let's go to talk show, today's talk show, and paste it here, link, and I want to, we need to put the formula for this. So let's copy the formula. Copy it. Go back to the page where this is. Go back to the page and oh, there's a Mathematica file there. Okay, so actually okay, let's do this one. Okay, there is a equation for the sphere. Let's try that as well. So okay, we don't need that. So let's try to plot that. Let's go back to Wolfram language. Now we are going to plot this. Okay, how do you do that? I believe it's contour plot. Okay. Yeah. Why does it not complete? Yeah, let's just type it. Yeah. Much better in Emac Lisp. So x from x min y max, x min x max. So we have a equation of 3 variables or function of 3 variables, you want to oh yeah, so x, y, z, those are what values or region. Produce a 3-dimensional contour plot of function as a function of x and y and z. So x and y and z are values. Let's just try it, okay? 0 to 2, okay? Let's just see what happens. Okay, that's not so good. Let's say this is what happens if when you do not exactly understand what you are doing. I'm not exactly understand what am I doing, just trial and error. And this is the fun part of using Wolfram language as well and learning mathematics. Okay, here we got kind of the contour plot. Okay, so we can see a sphere, so this is much more beautiful. So we need to understand what this function do. So let's try the other way, okay? So the other way is to say that f equals to g, okay? So here plots a contour surface for which f equals to g, right? So f equals to g, so that will be equals to 1. Let's try this, okay? Yeah, okay, so instead of, so negative 2 to 2. Okay, so what kind of thing is this? It actually should be 1 to 1. Okay, it's kind of funky. Okay, so we got the sphere we wanted. Okay, let's copy that. Let's just copy this. So where is the image? Okay, I want to put all images in a directory I, okay? Should I? Okay, let's not. Let's just put the images in the directory without an extra directory, okay? There you have it. This is your image. Okay, now let's put the equation below them. So here is the way you plot it, copy it. There it is, and Okay, now looks better. Now this old image, let's delete it. Done. Okay, let's open this Mathematica file. Zip file. Okay, let's show the directory. So here is a zip file. We're gonna unzip it in Emacs. Let's do it. Unzip. Okay, done. Open it. Now it generates a Mac OS, Mac OS directory. That's crap. Delete that, and remove all the backup files. Delete them. And so here is a notebook. Now this zip file we don't need. Open it, delete it. Okay, now this is the Wolfram language file, 20 years old. Let's open it. Open in external. Okay, so you can see this is done in 2005. Okay, continue with updated styling. Yes. Okay, so it requires a package, contours. Okay, parametric formula. So what formula was I using? Let's double check. So this is a bitmapped image. Oh, actually it's a PostScript image. So you see, we were talking about how in old Wolfram language, the grids on the surface is simply the edges of the polyhedrons. The polygons, not polyhedron. So cosine, cosine, sine, sine, sine. So it's using it's using the formula I was using. Okay, this notebook, we can delete it. So computer graphics methods of generation. Okay, in my old writing style, I'm kind of being verbose. Computer graphics method of generation. So actually, we forgot. Wolfram language actually has a sphere function by itself. So you don't actually need to plot a sphere. I forgot. Sphere is a sphere is a Wolfram language primitive by itself. So we can look at the documentation. You see, I forgot how idiotic I've been. So that's all you have to do in order to generate the sphere. Okay, so let's do it again. Paste it here. Do it. So but this sphere is so perfect such that you don't recognize it as a sphere anymore. It's just a color wheel or something like that. So this is interesting. This gets us to many interesting issues about illustration. So even though this sphere is technically superior because it's technically, as far as computer graphics is involved, it's more accurate, it's more smooth, it's more perfection with respect to all the properties of a sphere. But however, first of all, it's not recognizable as a sphere. You more see it as a circle, a color circle, something like that. Especially without without the bounding box. But however, if you see this image or this image immediately as human visual system, you see it as a sphere. And our job, typically in math context, we want to illustrate sphere for people to learn math, right? So this is not so good. we need to put on grids. Okay, so again, so here we need to look at the options of a sphere. Okay, sphere doesn't have options. Yeah. So now we need to look at, there's also a function of ball. What the fuck? So there's also a built-in function represents the unit ball centered at point P. So what's the difference between ball and sphere? A ball is known as center interval. Oh, okay. A ball is known as center interval, disk ball, and hyperball. Okay, so from this description, I gather the function ball in Wolfram language is more about geometry, while the sphere function in Wolfram language is more about computer graphics to illustrate a sphere. Okay. Right. So if you are doing mathematics, you might need to use the ball to represent a interval in 2D or 3D or 4D or 5D, so on, 5 dimensions. So ball is added in 2015. Okay. Now sphere is added in 2007. Okay. Yeah. So you see, sphere is a computer graphics related thing. It's more commonly needed, while the ball function is more mathematical oriented. It's added 7 years ago, 2014. So we are talking about partial differential equations and so on, this sphere. So let's look at a sphere. Okay, so come back to our question. For my purposes of generating an illustration for sphere, there's a question: which way to generate the sphere using Wolfram language is the best approach? And my guess is actually use the built-in sphere function. All we have to do is actually add the grid lines. But do we have options for grid lines for graphics 3D? I don't know. So let's check. So, we need to read a lot of Wolfram documentation. Okay, so, so I recommend Wolfram language. You download it for free. Why? Because, if you want to write this kind of thing in JavaScript, in any language, OpenGL, that's going to be 100 or more lines, 200 lines. Especially if you want this, if you want to plot a contour plot, that's going to be thousands of lines if you want this kind of grid on it. In Wolfram language, it's just one single line, or depending on how you count the line. So this can be a single line, or you count it as 2 lines or 3, a single line of code. So yeah, so it's great. So now let's look at how do you let's see options for graphics 3D. There are so many, and it's been a while. I looked at them. You have to actually study them if you really want to control your graphics. So graphics 3D, the following primitives can be used. Okay, the following graphics directives can be used. So you have absolute dashing, thickness, arrowheads. You have glow. You actually have glow, gray level, hue, opacity, specularity, thickness, line thickness specification. Okay, there are so many here. I don't think there's an option for grid. So let's go back to sphere. So there is no option for sphere, right? Yeah, option sphere is empty. So there is no option for sphere. But what if I want grids? So Wolfram language sphere function actually plots a sphere in arbitrary dimensions. Now I'm not sure exactly what does that mean, because you know, in order to represent the sphere in more than 3 dimensions, you usually have to do some kind of projection or cross section. So as far as I know, there is no such function that does, there's no built-in function to view higher dimensional graphics in Wolfram language. Maybe there is, I don't think so. Okay, sphere can be used in graphics and graphics 3Ds. In graphics, the point are scaled and dynamic expression. Oh, okay, so graphics rendering is affected by directives such as phase form, specularity, opacity. So what is a phase form? Okay, phase form is the one we use to control. There. Let's try that. No, didn't work. Edge form. So sphere doesn't have any edges and doesn't have any faces. That's why it does not work. Scope, graphics, specification. Styling, no, yeah, styling. Okay, it's only got colors. So it's funny, you know. So yeah, you got all these stylings, but none of them, you know, looks like a sphere, like the way we wanted. You just got this color ball, like a disc. Okay, so I think I have determined now that if you use Wolfram language, this simulates moon over rotating around Earth, you see. So I have determined that if you want to plot a sphere using Wolfram language for illustration purposes, you cannot use the built-in function sphere to do it. Because if you do want the grid lines on the sphere, this function doesn't give you that option. So here, how do I know? Because you read the documentation for the whole thing. So here, what is this one? It's interesting. Okay. Applications. Ooh, a bunch of kind of ugly thing. So I suppose this is, what is this? Platonic polyhedra represented by spheres. Okay, this is kind of ugly. In the early days, computer graphics, you have lots of this kind of thing. Extremely ugly. It looks like intestines. Okay, so can you actually magnify the whole. No, you cannot. Here we have double helix. Then we have, what is this? Then you have molecules. Properties and relations. Yeah, okay. So I decided that it is not possible to use the functions sphere and have grids on the sphere. Oh, okay. So Wolfram language gives you a example of a sphere using parametric plot, just like we did. Now it would be interesting to look at what parametric formula are they using. So we can compare notes. This is our original. It's ugly. Let's see what they did. Meshnan. I don't want Meshnan. Let's see their version. Okay. Same problem. You see, they got the same problem as we, missing a grid line. You see, so you are looking at the way I do things. I look at these details. I fuss around all these details of things. So this is their official documentation, and they are doing it to illustrate Meshnan. But however, they don't have an example showing how do you solve the grid line problem. Okay, so more molecules. Okay, so sphere, one of the great use of the sphere function is to represent molecule structures perfectly. You see, in this case, you don't want grid lines on the sphere, on the balls. Okay, no comments. No comments. I'm going to, so I'm gonna start to do next thing. So this is gonna be 1 hour or 2 hours. I need to work on this. So let me just, actually I do want an example of the sphere here. Let's see. Yeah, if you turn off the box, it's even. It's not, it's less comprehensible. So you do want the box. Yeah, I'm not going to have that. Okay, I'm not going to include that. So this is what we're gonna have now, for now. Okay, let's do the next one. So we've done sphere. Save this. Let's do the next one. Let's do this one. Okay, and let's clean up this yeah, our notebook. Yeah, our old notebook. Let's look at that. So here is another way by projecting. Okay, let's continue with this. Okay, this way is by projecting polyhedron. Let's see if we can do that. Polyhedra is a package like 20 years ago. It's obsolete. They have it built in by now. I think this will do it. No. Geodesic is not a type of graphics, okay? Okay, let's try to do this. This will take another 20 minutes. So dodecahedron. There it is. So basically we want to project the okay, so let me explain how do you do this. Okay, how do you do this image? You start with a dodecahedron, then for each surface of the dodecahedron, each face, you divide it into 5 triangles. Then for each triangle, you subdivide it into 3 subtriangles. So let's get fancy and let me show you, okay? And where is it? So using this pen, so you divide it into triangles 1, 2, 3, 4, 5. And for each triangle, you draw a point in the middle of the triangle, you subdivide it. So same thing here, okay? Same thing here. Same thing here. Same thing here. Okay, and you can continue the process. So again, for each triangle, you subdivide it like that. And this one here, and this one here. So once you have that, then for each vertex of the triangle, you project it into the sphere. Then you got this surface. Okay, we can do this. With this is 20 years old code. We can do it now by using built-in functions, and it'll be just one single line. But I don't remember. I don't know how to do it. I have to look, and this will take me 20 minutes about. So why not? Let's do that. Comments? No comments. Okay, I'm just gonna code myself. So first, we want to look into the dodecahedron's documentation. Okay. Actually, a better method, yeah, I made a mistake. Actually, the better method is not, okay, you can either use a dodecahedron to begin with, or you can use a isocahedron to begin with. So isocahedron looks like that. But anyway, what I'm looking for is to triangulate triangulate the surface of the dodecahedron. Okay, let's look. Okay, this is gonna take me a long time. This is going to take me 20 minutes to read about all these. So what I want to do, I want to generate these graphics. And in order to do that, let's see. Okay, it's a bitmap image. In order to do that, you know, like I said, I'm gonna, the way I did this one is to geodesiate. Yeah, to break the face into triangles, then project them onto a sphere. Now, what is the function to do that? Let's see. Polyhedron data, uniform polyhedron. Okay, so I need to read about polyhedron, collection of polyhedron. Okay, let's just look at that. Polyhedron coordinates, outer polyhedron, inner polyhedron, cube, dodecahedron, icosahedron, octahedron, blah blah blah, hexahedron. Hexahedron is just a cube. Oh, okay, so regular hexahedron is a cube. So, but the hexahedron function in Wolfram language actually represents a generic hexahedron. So it needs not to be a cube. It can be any, you know, cuboid basically. Canalized polyhedron. So what does this do? Inner boundary, outer boundary. Okay, I'm getting tired actually. So polyhedra, let's see. Polyhedra. So back to polyhedron, let's see what else they say. Mesh region, random polyhedron, polyhedron data, simplex. So let's see mesh region. What does mesh region do? Oh, here we have something similar what we wanted. So what is this? Rendering feature themes affect the rendering of meshes. Themes include large mesh, optimized for large number of cells. What is this? Mesh region. Mesh region yields a mesh with cells that where coordinates given as integers. I am pointing taken. Oh, there it is. Triangulate mesh. You see, this is what we wanted. Triangular mesh generates a triangulation of the mesh region, MR. So mesh region is a particular object, entity. Now, I don't quite understand what exactly is a mesh region with respect to the Wolfram language. Okay, so here is an example. So you can the triangulate mesh function can generate a triangulation for you of a mesh region. Now, what exactly is a mesh region? I don't know yet, but basically, it's basically a rectangular patch or a triangle, something like that. So boundary mesh region. So okay, so it allows you to do this kind of computational geometry, triangular mesh. It's fantastic. So now knowing there is this function where you can generate a mesh arbitrarily, you see, now we revisit the way we, this one. The way we did it here is by a regular means, breaking a triangle into a smaller, 3 triangles and into smaller 3 triangles. These results, this way is not necessarily ideal because then you get a triangle that's thinner and thinner. So, like very thin triangle. But if you do it this way, it could be better. So triangular mesh, and maybe you want some way to make it regular. Of course, we can also do it ourselves by, okay. There's a problem with, let's see, F11. Does the F11 don't work? No, F12. What is F12? Okay, I think there's a bug. Okay, so I think there's a bug with the Windows. Let's try again. F12. Yeah, it doesn't respect your Windows so well. Oh, that's probably because I have the Windows taskbar on top. You see, this is a problem of doing, this is a problem in software industry. You have, you have a problem. You see, my problem is that the Windows, sometimes it goes out of the place. I cannot access to the Windows bar or, to manipulate the window size, and Alt space sometimes doesn't work. We ran into that problem earlier. And then now it turns out, it's possibly because I was using auto hotkey. So because you don't know where is the problem. For example, let me show you my auto hotkey. Where is my, so this is auto hotkey. Let's qualify it. Okay, so here's my auto hotkey file, and I have a function that toggle maximize window, which is fantastic because it's unlike the normal toggle. The normal on Windows, you press F11, you don't see the tabs and all the other things anymore. So for example, if I'm in a browser, press F11, you don't see all those widgets, but you actually, it's better if you do, so you can see all the tabs. So this is auto hotkey. So, but now I run into a problem in Wolfram language. I don't know if it's maybe caused by auto hotkey or it's something. But maybe now I'm thinking maybe it's because of because I have the Windows bar, the taskbar on top. So Wolfram language, the mathematical application gets confused. Let's see if this works now. Okay, maybe yeah, that's why. Let's do it. Let's see. So here's another lesson: the complexities of the fucking software industry. The complexities of software industry. So you think, oh, I can make the taskbar on top. But then you got problems. You got all these glitches. Okay, so let's see. Okay, so now I'm going to continue. Work on this. yeah, I'm just going to continue read about mesh. Maybe that's it for today. So I need to do a lot of readings about the mesh in order to do this using the latest Wolfram language functions. Yeah, that's it. Thank you guys for watching. Bye.